Hey everyone, welcome to April 20th recitation. So today we're going to be looking at three problems from the PDF of the assignment. So we have one from 5.3, 5.4, and 5.6. So to start off, let's look at this one from 5.3, which is asking us which values of h for this matrix here, 2h0, 2, allow it to be diagonalizable. So we have to figure out what h's would make this diagonalizable. All right, let's start off by finding the eigenvalues. That's usually a good place to start for problems like this, and it gives us a little help as to nudging us in the right direction. So if you want to do that, we just need to take the determinant of, we're going to call this a, we need to take the determinant of a minus lambda I and set it equal to 0. So that's going to be 2 minus lambda, h, 0, and 2 minus lambda. All right, and if you take the determinant of this, you end up with 2 minus lambda squared. The negative h times 0, that just ends up being 0, and we set it equal to 0. This ends up giving us back lambda equals 2 with a multiplicity of 2, so it gives us 2 twice. So when we have repeated eigenvalues, there's a theorem in the book that helps us understand how that relates to its diagonalizability, and that is theorem 7 here. So specifically, I'm interested in B. It's given that A is an n by n, whose distinct eigenvalues are lambda 1 through lambda p. All right, so for this one, A is a 2 by 2 matrix, so n equals 2. And lambdas go through p, and we only have one lambda, actually, only one distinct lambda, so p is 1. Okay, so we're looking at part B here, or part B of this theorem, and it says A is diagonalizable. Okay, that's what we're interested in, if and only if the sum of the dimensions of the eigenspaces equals n. All right, so what does that tell us? Well, we only have one eigenvalue, so we're only going to have one eigenspace. So we're not really concerned with the sum of the dimensions so much as just the dimension of the eigenspace here. And it has to equal n. Well, n is 2, so we're saying that the dimension of the eigenspace that corresponds to lambda equals 2 needs to have a dimension of 2. It has to be 2. All right, and this goes on to kind of repeat what we said, the rest of this. So, but we're really interested in, proving this. So if we need to find the dimensions of an eigenspace, that is the same thing as just putting this all in a matrix here. It's going to be a minus lambda I again. So this is going to be 2 minus 2, h, 0, and 2 minus 2. And we're going to augment that with 0, 0. So reduce this, and we end up with 0, h, 0, 0, 0, 0. All right. And now the question being asked is, how can we let the dimension of the eigenspace be 2? All right, so let me go to typing here now. All right, so we want the dimension of the eigenspace to equal 2, right? So that's equivalent to saying we want 2 basis vectors, right? That's what a dimension is. It's how many basis vectors would you have for a space. So 2 basis vectors. All right. And notice we're dealing with finding the basis vectors right now. You should be pretty familiar with the process of getting the basis vectors for an eigenspace. So basically, that's like saying we want 2 free variables for a minus 2i augmented with 0. That's the thing that we set up here, right? It's a minus 2i augmented with 0. So if we can set this up in such a way that we get 2 free variables, so what would that look like? That would look like we'd have a solution with x equals some vector x1 plus some vector x2. So the solution would be this. Now the question is, what would h have to be? what would we have to set h equal to that allows this to happen, that allows us to have these two free variables? So that's the question that you're going to have to figure out. What value or set of values for h gives you two free variables when you reduce this? So I'll leave that one to you to work out. But the explanation would basically follow this chain of logic, and you could even mention this theorem in there, that we need a two-dimension eigenspace. All right, for the next one, we are, and I started writing some stuff here. Let me just erase that. Right, so we are looking at a basis B, and we are looking at a linear transformation T that sends it from vector space V to vector space B. And we're looking at bases B and C. And we want to verify that these matrices, so this is the linear transformation matrix with respect to B and with respect to C, are related by the following relationship. So we're using these two change of base matrices here, P from B to C and P from C to B. And then we're given a hint too. And I think one of the helpful things that this hint gives us, and you can pause and read it, but one of the helpful things the hint gives us is that B of I is essentially what we're worried about here. When we're talking about doing all this, this sort of transforming, what we're really interested in is how does this affect some matrix BI if we were to multiply this. And BI, for the space B, BI reflects all of these basis vectors. So B is going to have basis vectors B1, B2, all the way up to some n for however big the dimension is. Right? So we can find these, and these all would really look like something we've seen before, right? Because we're talking in basis B. So the basis always looks something like, and I'm just going to draw 3 of these. We don't know the true dimension, but just as just for instance, this would just look like E1, E2, E3, right? With the zeros and then a 1, because we're expressing the basis in, in base B. All right, so we have that. We have that the BIs are going to look something like this. And we know that we want to show that multiplying them into this gives us the same thing. So what I would suggest thinking about here is multiplying some arbitrary BI on both sides. So here we would multiply a BI with respect to B. And over here, what do we got? We have P from C to B. We have this linear transform matrix expressed in terms of base C, so it's going to be different. And we have P from B to C. And finally, on the right, we're right multiplying some arbitrary base of B on both sides. So your task then is to show that for any arbitrary BI, whether it be the first, the second, all the way up to the nth BI in this vector, to show that it will multiply out to give you the same thing on both of these sides, even though you're using a different linear transform matrix. Here it's T with respect to B, here it's T with respect to C. So you want to show that by sandwiching this T of C in these change of basis matrices, you're actually accomplishing the same thing. So as a start, we can consider what would it look like if you multiplied these two on the right. We have P from B to C and BI of B. So remember, this is the change of basis matrix from B to C. So if you apply that to BI of B, then all we're going to have is BI now in terms of C. All right, and then the rest of this is the same. We still have P from C to B, and we still have T of C. On the left here, I'm going to multiply these together. So this is like getting a product. We're going to take T BI and just say that that's in terms of B. Now remember, and this might be important to your interpretation, this is essentially the same thing as the ith column of t. And if you don't believe me, try, and I think you should try, doing it out with actual ones and zeros and, some example t, and seeing that you end up getting back the ith column. So this is the ith column of t, is what that will return. And more specifically, this is the ith column of tb. All right, over here, we have p from c to b. And we're going to be multiplying these two together. So we're going to end up with tbi with respect to c. So what is this then? Because we already talked about, we talked about what this was before. So this is going to be, we have t in c, so it's a totally different matrix, and we also have bi in c. So it's not necessarily going to be ones and zeros. It could be any kind of vector of length n. We just really don't know. But what we do know is that it is t times bi in c, and we know over here this is t of bi in b. So we know that the only difference between them is the fact that they're expressed in a different base. All right, so I think the last step of this would be to show what happens when you multiply the change of base matrix from C to B into this, and show what you get. And then maybe a little bit of an explanation as to why this shows what it shows, why proving this for some arbitrary B was enough. And I'll give you a hint that, if you're interested in proving this for any matrix, I don't know, say 7, 3, 6 or something. And we want to show this is true. Maybe I should say 7, 3, 6 in B. All right. So here we're just pretending that B is dimension 3. Well, this is the same thing as 7 B1 plus 3 B2 plus 6 B3, right? And because T is a linear transformation, the transformation of this should be the same as the transformation of 7 TB1 plus 3 TB2, and so on and so forth. So by showing that this, this transformation can be done with respect to either vector, you're kind of, you're proving that this works for any vector in B. So an explanation of that would be good. Finally, one sec. All right, now for the last problem here. So we have 3 from 5.6. Okay, so to start off, we are being asked about a steady state vector for A. So what I will say for this one, we know that the steady state vector has to have an eigenvalue of 1, and it also, and it also has to have an eigenvector for which the sum of the values is 1. So I don't know exactly how to write that, but you could think some eigenvector and the sum of all these values must be 1. So we can do that, right? We know the fact that if we have an eigenvector, we can scale it by some constant to do whatever we want. So we could just basically turn it into a unit vector, right, by dividing by something. So we're not really worried about that. What we are worried about is seeing what this eigenvector actually is and how to find it. Right. So we know, though, that if we want to find an eigenvector, and we already know that one of the eigenvalues is 1 because it's given to us, all we have to do is set up A minus lambda I. Here, lambda is just 1, so I'm just going to write A minus I equals 0. Or maybe another way would be writing it so that we're augmenting it with 0. So if we were to actually write it out, we would have negative 0.4, 0.4, 0.4, 0.3, 0.3, 0.5, or I'm sorry, this should not be a 0.3, this should be a negative 0.7, right? 0.5, and a 0.1, 0.3, and then a negative 0.9 because we're subtracting 1. All augmented with zeros. All right. So I'm going to let you figure out what this would be. But know that when you solve this out, you should end up getting at least one free variable. And that will allow you to determine some v. So we'll call it v1. And I'll also make a note that, so right, v1 is going to have 3 elements in it. And I will also make a note that, remember, the elements in this have to add to 1. So they have to add to 1. So if they don't add to 1, figure out what you would need to divide it by to force it to add to 1, because we're talking about probabilities here. All right, so part B then. So, once you found this vector v1, you're good. You found the value for part A. You could even test it, and maybe it's a good idea to test multiply A by V and show that you get V back, right? So now we have part B. Okay, in part B, so this is actually about the weather, right? We're given the weather in Columbus and a probability vector that predicts what the weather will be in the future. So it says the weather today in Columbus is indifferent. Assuming the model, what is the approximate probability that 1 year from now, 365 days, the weather will be good? All right. So this plays on a lot of the things that are shown in 5.6. Similar to problem 2 from the book, sort of, from here on. So we have this, we know that there's this polynomial we can sort of form to predict new values of x. And it looks like, let me make sure I'm getting it right. So it looks like x sub k plus 1 equals c1 times lambda 1 to the k, k plus 1, v1 plus, and then it goes on, and it does this with all the c's for however many eigenvalues there are. We have, well, I guess we don't really know how many eigenvalues we have. So that is something we have to find. I'll tell you right away. There's 3 eigenvalues for this one. I guess you can kind of know because it's a 3 by 3, and because they're asking this, we have to be able to diagonalize it. So we know that we're going to be able to find 3 eigenvalues. So I'll denote them. Lambda 1 is 1, and then there's lambda 2, which we don't know, and lambda 3, which we don't know. Okay, so that's your first task. Find these. Okay, and then once you've found your 3 eigenvalues, next thing you want to look at is what are these constants, C1, C2, and C3. So we know there's going to be C1, and then I didn't write them, but C2 and C3. So the way to get those is using the eigenvectors, right? So we are going to set this up in such a way. Well, first off, we want to use x0, right? We're given an x0 here. So we're going to set k, I guess, equal to like -1. You could think of it. All right, so if k plus 1 is 0, then here we have c1. Lambda to the 0 is just going to cancel, and we'll have v1. We'll also have c2, v2, and c3, v3. Now, what are v1, v2, and v3? Well, those are the eigenvectors. v1 you've already found up there. v2 and v3 you have to find. So that's kind of your next step here, is to find the eigenvectors, v2 and v3. All right, so that would be your next task. This is all pretty simple stuff that you've been doing. Right, so, all right, you find those eigenvectors. Now you should be able to set this up as a matrix and find the C's from that. So this matrix will just look like V1, V2, and V3 in the columns. And the last column, which will be X0, X0 is given to us as 0, 1, 0. So I would reduce this, get I, and then whatever. The thing that you'll be left with are your constants, C1, C2, and C3. So this is your next step, is using these eigenvectors that you find to get your constants. Once you have that, then you can set up your equation here. All right, so I know at this point we're being pretty abstract. We don't really have numbers, but that's okay. We can look at this. We can look at this without thinking about the the exact eigenvalues. So if we were to set this up, given our constants and our v's, the next thing they want us to do is to think about large K, right? We're looking at X365, 365 days from today, 1 year in advance. I would say that qualifies as large K. You can read a little in your book to see what these problems look like for large K. But basically the idea is we're looking at which terms kind of dominate this expression. So say lambda 2 is, for instance, I'm not saying this is true. So let lambda 2 equals 1/2. That would mean that one of these terms in here, the C2 term, is going to look like C2 times 1/2 to the 365th power, times some vector V2. If you multiply 1/2, and you can try it, if you keep multiplying it by itself, it'll get smaller. You'll get 1/4, 1/8, 1/16. 1/2 to the 365th is so small that it's almost negligible, and it pretty much is negligible for the case of trying to predict the weather. And this makes sense, right? If you have a small eigenvalue here, this would intuitively suggest that you can't predict the weather a year in advance to that level of precision. So what we might expect to find is that one of these eigenvalues or one of these eigenvectors is sort of like a normal weather, like an average prediction. Something that you might say, what's the weather a year in advance? Well, what's the average weather look like on a day like today? Because that's your best bet. And then the other two are going to essentially be useless over a long period of time. So that would be indicated by eigenvectors or eigenvalues, sorry, that are fractions. So your job here is to figure out which term dominates it. So x to the 365, or I should say x to the k plus 1. And you should be able to find that this is equal to some constant times x to the k over a long period of time for large K. And then once you found that, then I would say, it would be a fair bet to say, all right, this is the most likely weather over a long period of time. You can then from that figure that the vector that's given to you would be a good approximation of the weather. So whatever a vector is in the dominant term, V1, V2, or V3, that would be your best bet. So it's going to be V1 or V2 or V3 is going to be your best prediction vector. And you have to find which one. So which term dominates is equivalent to saying which eigenvalue is not a fraction. All right, so hopefully that makes sense. That one's definitely a tricky one, and there's a lot of sort of intuitive thinking going on. So I find that leaning into the weather analogy that they're using here actually kind of helps it make a little more sense than just abstract steady states. Yeah, so good luck with the homework assignment. Have a good rest of your week, and I'll see you guys next week.